let's get started. Here we go. Have your attention, please. Okay, so we've done a lot of work in this course, and I'm going to take about 10 or 15 minutes to tie together everything we've done so far. This next little discussion is really, really important because it brings together all these huge principles that we've been dealing with, right? So calculus is a coherent body of knowledge with a goal. It's not first chapter with some exercises, and then second chapter with some exercises, and then chapter 3 with some exercises, okay? Calculus has a pinnacle idea, and everything we've been doing so far is going toward this pinnacle idea. So let's talk about that. So we really have seen a circle of functions. So f of x, r sub f of x, a sub f of x, back to f of x. Okay? We know lots about this, or we should, okay? So f of x, starting with an amount function. It gives some amount, right? That's the dependent quantity. That would be the value of f of x for any value of x, which is our independent quantity. Okay, so when we talk about dependent and independent quantities, we could be talking about some time quantity, volume, temperature, weight, distance. Okay, all these are quantities, right? And so we've got some, maybe this is distance from a reference point as a function of time. Distance from a reference point as a function of time. That's like an amount function, okay? But there's all kinds of quantities in the real world. So what I want you to do here is, I want you to take about 5 minutes or 3 minutes, talk about each subsequent function. So r sub f of x. What function is that? How would you define that in general? And how do we get it from the previous one? Mathematically. Mathematically, how does it stem or become derived out of the previous one? And you do that for all three. So what is r sub f of x? How do we get it from f of x? Mathematically, how do we actually attain it? And then what is a sub f of x? How do we get it from r sub f of x? What is it and how do we get it? And then finally, what is f of x and how do we get it from a sub f of x? Really important conversations. So we all should, if we're going to be experts in calculus, we really need to know this. So talk this out with the people around you, and then if you have questions, we'll also circle around. But super important. Go. What's the function? How does it come from the one before? Where is Nicole Ballin? Nicole, tell me about r sub f of x. First of all, what function is that? Rate, okay. Is it exact, approximate? Exact, she says exact rate of change. Is this right? Exact rate of change function. Okay? And how do we get it from f of x, or how do we derive it from f of x? Okay, and how mathematically, what does that rate between 2 points? What is that? Do you remember? Yeah, Good. Okay, so this is the exact rate function. This is f's exact rate of change function. It tells us how fast the dependent quantity is changing at every moment, how fast it's changing every moment, and it can be written as, found as, what she said, f of x plus h minus f of x over h for h when h is really small, or small enough, so that we can't tell the difference between exact and approximate rate of change. Are we good? Okay, cool. So now the next one is a sub f of x. Where's Lufin? Chen. Lufin. Are you here? Not here. Catherine Riordan. Yeah. What is a sub f of x? What function is that, first of all? She wants exact net accumulation. Agree? Yeah, exact net accumulation. What is that? What is exact net accumulation? Can you describe what that is? Okay. Is it accumulation of rates? Are we accumulating rates? So this is a common thing that students will say, that we're accumulating rate. Are we accumulating rate? No, what are we accumulating? Rate times change in x, which is we're really accumulating changes in y, changes in our amounts. We're accumulating changes in y, which are found by rate times change in x. Okay? So this is the exact net accumulation for the accumulated changes in f starting from x equals a. And this can be written how? Let's see. How can we write this? Where's Thomas LaCour? Yeah, Thomas, how can I write the exact net accumulation function given r sub f of x? Not sure. Okay. Where's Sarah Erickson? Do you know how we can do that? Given r sub f of x, how do we write the exact net accumulation a sub f? Just r times change in x. This is what y initial is. Okay, so this was the question. This is what we spent most of September and October on. You know how fast the quantity is changing at every moment. You want to know how much of it you have at every moment. And our grand conclusion to that was, where is Hannah Lou? Hannah. Yeah. One more time. No. Let's see. I have it in the middle there in the pink shirt. Okay, yeah, 99%, right. You made a little mistake. What was that little mistake? You can't, the x's can't agree, right? So you can't use x. Right, so this was the big conclusion from our long journey of, you know how fast something is changing at every moment, you want to know how much you have at every moment. So the exact amount that you have at every moment, we came to the conclusion was the integral of r sub f t dt. And when we look at that, it reminds us of what? What do we think when we see that? Yeah, Charlie. The long a function, right? The long a function that was accumulating all those little changes. So when the changes in our independent get really small, we have this compact notation for that. Okay, so this is essentially that long a equation that we worked hard on for very, very small changes in x. But we still see the idea of it, right? It's the sum of what? dy's, m dx. It's the sum of, right there is constant rate of change, m dx. And we're going to sum up a bunch of results of lots of little m dx's. Okay, and so then now we have the exact net accumulation function. And where is Jared? Jaiwei Wu. Yeah, so then now that we have the, what is the function f? And how can we get it from a sub f of x? What is the function f? For the what? The whole amount? Yeah, okay. And how can we, so we called that what? From exact net accumulation, we called that, yeah, Robert.
You take the integral that was listed for the exact net accumulation and take off a, so it would be the integral from a to x, r sub f t times dt minus f of a.
Okay, you're on the right track. Where is Logan? Lahi. Yeah, Logan. Oh no. Where is Dylan Jacobs? Dylan. Yeah. How did we get f of x from a sub f of x? Or what was it? First of all, what was it? We still really haven't decided what was f of x related to a sub f of x. If a sub f of x is exact net accumulation, then f of x was what? What did we call that? Do you remember what that was? You had raised your hand. What's that? Yeah, which accumulation function is it? Lots of hands. Yes, sir? What's that? No, we're just identifying what function this is behind them, yeah.
The exact total.
Exact total accumulation, right? If this was the net accumulation, then our F was the total accumulation, which means we might have what? Some initial amount. Initial accumulated amount, which we call F of A. All right, so this is the amount function, right? So this is the amount function, but now we're taking the perspective of accumulation. So a final amount is just the total accumulation that you got up to that point, right? So the final amount that you have is just can be seen as how much is accumulated up to that point of X. And we can write that as the net accumulation, what? Plus F of A, right? Plus F of A. So, and this brings it, like I said, this brings us back to amount. So this is the total accumulation, which is whatever total amount is accumulated, well, that's what you have. That's your amount. And that takes us back to F of X. Okay, so what do we have? We have F of X is equal to F of A plus. All right, so what was this? Amount is same as total accumulation. Anything that accumulated before A plus little amounts accumulated starting from A to X gives your total amount at X. Should make perfect sense, right? Your total amount at X is whatever's accumulated, or the amount at A, plus the accumulation starting at A to X. And this shows that using the rate, okay? So if this is true, then look what we can do. We can I can solve for that accumulation. So if I solve for that accumulation, we know this is what? This is the net accumulation. The net accumulation starting at A up to X. So say of F from A to X. And what will that equal mathematically? F of X minus F of A. And so what is, when you take one final value of a quantity minus the initial value of a quantity, what do you get? Total change in F, right? Total change in F starting from A. So it's the same value, but it's kind of two different perspectives on it. So this perspective is a little bit of accumulation at a time, summing up to an amount of change, right? A little bit of accumulation at a time, mdx plus mdx plus mdx, all right? Summing up to some total amount of change. Well, that total amount of change is what? The final amount minus the initial amount. So that's the total change in F from A to X is equal to the net accumulation of changes in F from A to X. This makes perfect sense. Does it make sense? All right, so for instance, if my son is, at the end, he's 37 inches tall, and when we started measuring, he was 32 inches tall. That's like final amount of the quantity minus the initial amount. Well, that equals some sum of a bunch of tiny little changes in his height, starting from 32 to 37. So that's the idea of integral, okay? And that sum total of the changes would be 5 inches. 5 inches. Okay, so here, and this is the key now. This is the key to when we got to the end of this journey of figuring out exact accumulation. We said We only have it in open form. How we want to get these accumulation functions. Given a rate, we want to get the accumulation function in closed form. Well, this is the key. We can write it as f of x minus f of a. So this will be our ticket to writing a closed form for the open form accumulation function, which is the integral. So this is the key to writing accumulation functions in closed form. We need to know the amount function from which the rate came. So that's why we started the reverse process. You see? We started the reverse process and we found out that we could write rate functions in closed form given the amount function. That's what we're working on now. We're working on given an amount function, write the rate function. Every time we do that every time we get a rate function for an amount function, then we can construct a closed form for that open form accumulation function. The one that's the integral of that rate function dt. So what do? We said if for instance, if the volume of a sphere was 4/3 pi r cubed, we found out that r sub f was, we did the math, and we found out it was 4 pi r squared. But when we did that, we found out two things. We didn't only find out that the rate for the volume of a sphere, the rate of change of volume was 4 pi r squared, but we also found out that if we had the open form accumulation function, say from, keep going with red here to keep it separate, so we not only found that this was the rate function for that, but we found if we came along to an integral like this, say from 2 to x of 4 pi t squared dt, we can write that in closed form now. So this is an open form accumulation function. We're able to write that in closed form now with what we just concluded. So can you do it? How would we write the integral from 2 to x of 4 pi t squared dt in closed form? Take a minute, see if you can do it, and we'll regroup. But see if you can do that. So you're going to apply this stuff over here. So according to this, f of x minus f of a is the integral from a to x. What is the integral from 2 to x 4 pi t squared dt? Did I call on Dylan already? You want to try this one? Okay, so we're just going to apply this. We're just going to apply this. We're just going to apply this right here. What does an integral from a to x r of t dt equal? Just apply this. Equals means they're the same. So what does this equal? Just apply it. Yeah, go ahead. F of x minus f of 2. But here's the key. We know what f is. We know what f is, right? What is f? 4/3 pi r cubed. So this equals 4/3 pi x cubed. And what's f of 2? You don't have to solve it in your head. 4/3 pi times 8. Closed form. Did you catch it? See what happened? So before we started the reverse process, we were stuck here. We were dead. We knew what it meant. We knew it was the accumulated changes from 2 to x when the rate was 4 pi t squared, but we couldn't get a closed form. Now we know that's equal to what? The amount function evaluated at x minus the amount function evaluated at 2. And we know what that amount function is that has that rate because we evaluated that. So now we can just apply the amount function, f of x minus f of 2. And then we got closed form. Does it make sense? Super important idea. So in this reverse process, we want to get as many closed form rate functions as we can because every time we get a closed form rate function, we can write an open form accumulation function in closed form using that. So we also did what? So we did the area of a square. So I'm gonna do a new example here on the right. Questions on the volume example. So we also found what? That the area of a square, I'll call it capital A sub x. What's the area of a square? Easy one, right? X squared. And what did we find? Do you remember what we found for r sub a of x? We worked that out last time in class. That was 2x. Okay, so that means we could because we know that the rate of change of x squared is 2x, we could now write this open form accumulation function in closed form. So I'll erase all this stuff here, and you're going to do it now. So I want you to write the integral from 7.5 to x of 2t dt. Write it in closed form. Where's Austin Baker? Austin, can you help me out here? Okay, and so what would be the intermediate step there? That's right. Okay. Is it f of x minus f of a? So if I want to use function notation for this, what would the function notation be? Yes, in the green back there. A of x minus a of 7.5. And then that's what, Austin, that's what you said. What's a of x? X squared. A of 7.5 is? Okay, and so relative to the square, what is this function calculating? What is this function calculating relative to a square? If it is at the integral of 7.5x 2d dt, what is that? Or x squared minus 7.5 squared. So I want you to have a conversation. What, relative to a square context, what is that getting for us? Go. Okay, where's Chandler? Chandler. Yeah. What did you talk about? So what? What does x squared minus 7.5 squared mean? What does that get for us relative to the square? Net accumulation? What net accumulation? Exact net accumulation. Okay, which one? Aiden. Okay, so now it's like we're starting with a square that has side length 7.5 and area 7.5 squared, and this function is going to calculate what? The change in area. The change in area starting from a square that's 7.5 side length or 7.5 squared area. Same thing with this, but this just does it. This just represents it as the accumulation of changes in area starting from a square with side length 7.5 up to a square with side length x. So that amount of accumulation is then going to be the total amount of change in the area. So the total amount of change in the area is the amount of accumulated changes in area starting from 7.5 for side length. Okay, so for this reason now, the next thing we're going to do is we're going to find as many closed form rate functions as we can. That's the goal in the next couple of weeks, and that's the idea of the mastery test. The mastery test is it's just this exercise in your memorization of lots of rules that can get us lots and lots of closed form rate functions, because every time we get a closed form rate function, we can write an open form accumulation function in closed form. Every time we get a closed form rate function, we're able to write an open form accumulation function in closed form by the reverse, right? The reverse. Okay, so this very important thing, the most important thing in our course is called the fundamental theorem of calculus. Everything we've done so far has been up to work to this. It's so important, I'll put 2 boxes around it. And even a star. Why? Because it brings together rate and accumulation and amount, and it allows us to get a closed form accumulation for every closed form rate that we have. Okay? Questions on this really important discussion? Okay, so let's talk about, like I said, now we want to talk about getting as many closed form rate functions as we can. Here we go. I don't know where I am. Let's see here. Let's try this one. Okay, so let's talk about constant functions. So constant amount functions. If the accumulation f never accumulates any changes in its value, it's constant. What's its rate of change? A couple people think 0. How fast is something changing if it's not changing? What number? 0, right? So let's show it mathematically. So if we want the rate of change of f, for f is a constant, so we have f of x is a constant, and now we want the rate of change of f. How can we mathematically figure out what the rate of change of f is? This is what we've been working on the last week. We've got a function f. What is its rate of change? Derek Tran. Derek. Yeah. If we have a function f, how can we write its rate of change?
Well, since the rate of change is 0,
No, we need to show that. So we're not assuming that to start with. So we don't know what the rate of change is. We want to write out a mathematical statement that gives us the rate of change of f. Not sure. Okay, where's Bjorn? Building. Is Bjorn here? Astrid. Yeah. I've got the function f. I want to write its f rate of change. Yeah. Yes, good job. F of x plus h minus f of x. Okay, so and then that's for what? When h is essentially 0, really, really small. Okay, we get the exact rate function. This is our bedrock. The rate of change will always be this. It's always this. F of x plus h minus f of x over h, no matter what the function f is. So this is always the place to start when we're looking for a rate of change. This is always the place we start. Okay, so if f of x is c, then what's f of x plus h? C. This says no matter what your value of your independent is, the output is always c. Doesn't matter what your independent variable is, you always have c. So what's f of x plus h? And what's f of x? C. Therefore, a rate of change is 0. Easy proof, right? Easy proof of this fact that should make sense, that if it's not changing, the rate at which it's changing is 0. Okay, so all constant functions have a rate of change of 0. Add it to the list. Here we go. Next one. Constant multiple. So let's think about the premise of a constant multiple. If at every moment in time John has traveled 5 times as far as Mary, what can we conclude about John's speed relative to Mary's speed? So now this is thinking about distance as our amount and speed is our rate of change. So if his distance is always 5 times as far as Mary's distance, then what about his rate of change, his speed compared to Mary's rate of change? Very logical. 5 times as much. So what does that mean for us? So if f of x is John's total distance after x hours, Mary's is g of x. What do we know about the distance? So this initial statement tells us how are f and g related. This initial statement, John has traveled 5 times as far as Mary. How could we write a statement for that? Where is Jasmine? Yeah, Jasmine. So John has traveled 5 times as far as Mary. So what's the relationship between f and g? You got a good start there? F of x is? Yeah, 5g, right? And then what does this statement say? At every moment in time, John's speed is 5 times Mary's speed. So what does that statement say? How can we write that mathematically if we got our functions f and g? Where's Laurel? Chappelle, Laurel. So mathematically, what would the statement John's speed is 5 times Mary's speed, how could we write that mathematically using these functions we started with? Where's Laurel? Yeah. So if f is John's total distance, what's John's speed? How can we write that as a function? What function is that? Yes, sir. Yeah, yeah. Oh no, we just want to rewrite this statement right here. That John's speed is 5 times Mary's speed. So that's right, r sub f of x is John's speed. So what's the mathematical statement for this right here? Yes, ma'am. In the gray back there. Yeah. Gray shirt. Right. So that second statement in red is this one here. So the premise was that one quantity is 5 times another quantity, or one amount is 5 times another amount, and our conclusion is that the rate of that first amount is 5 times the rate of the second. And that was just a common sense. So this is not, we didn't do any mathematical proof. You're actually going to do that in your homework. So you're going to, as part of a little homework exercise, to prove that mathematically. Okay? But beware of assuming what you're trying to prove. You can't assume this. This has to be your final conclusion. So you're not going to write anything that's equivalent to this along the way. Okay? What you are going to start with is just what is r sub f of x? What do we know for sure r sub f of x is? That's how you're going to start. And then from there, you're going to apply what we know here in the given to say that that's equal to 5rg of x. Okay, so that's a little homework exercise. You're going to prove this constant multiple fact. That whenever one function is a constant multiple of another, the rate of the first function is the same constant multiple of the rate of the second. Okay, questions on that? Don't have time for that one. Let's see if I got the sum now. Okay? The rate of change of the sum of two functions. The rate of change of the sum of two functions. So what would it be really nice if it were true, right? So if kx equals fx plus g of x, and we're interested in r of k of x, the rate of change of k with respect to x, it would sure be nice if it were what? Yeah, Kyle. I don't know what combination means. Sum. Yeah. So what would it be? It sure would be nice, wouldn't it? If this were true. So where do we start? We start with the fact that r sub k of x is k plus h minus k of x over h. All right? We know that for sure. This is what we know. That we know if we have a rate, if we function k, its rate of change is k plus h minus k over h. We always start with this, what we're certain about. All right, so what is k of x plus h? What is k of x plus h? Do you know? What is it? Right, so this, if it's k of x plus h, it's going to be f of x plus h plus g of x plus h. And we know what k of x is, right? It's f of x plus g of x. So this thing simplifies to this. What? Oh, simplifies. Doesn't, yeah, right. Expands to, I guess. That's not hard, right? We know that this is true. So k of x plus h is simply f of x plus h plus g of x plus h minus k of x, which is f of x plus g of x. And where are we heading towards? We're trying to get that this thing is equal to r sub f plus g sub f. Can you almost see it? What are we going to do? We're going to gather together the f part and gather together the g part. So all I did now is I just took the f of x plus h and the f of x and gathered them together. The g of x plus h and the g of x gathered them together. And so what do I have? Can you see it? What is f of x plus h minus f of x over h? What is that? No. That's the rate of change of f, right? That's the rate of change of f. Do you see it? And then what is g of x plus h minus g of x over h? This is exactly what we hoped for, right? So you gather together your f's and your g's, and you get the very, what? We get our rate of change of f and g. Okay, again, this is when h gets really small. Okay, so we have these three so far. We don't have that one yet. But we have, if you have a constant, the rate of change is 0. When you have one function that is a constant multiple of another, the rate of f is that same constant times the rate of g. Now, students mix this up all the time. Watch out for this. They want to say, oh, there's a constant there, so the rate of change is 0. No, when it's multiplied by a function, the rate of change is that same constant multiplied by the rate of change. It's only when that constant is hanging by itself that its rate of change is 0. And then we know the rate of change of the sum of functions is what we hoped it would be, the sum of the rate of changes, right? When a function is a sum, the rate of change of the function is the sum of the rate of changes, which we just showed. Okay. So so then the mastery is going to be delayed 1 week like all the other exams.